In 2006, 424 astronomers gathered in Prague and took a vote. In less than 90 minutes, they erased a world, but here is what they did not tell you. At the exact moment they were voting, a spacecraft was already being assembled, one that would spend the next 9 years crossing 4 billion miles of frozen darkness to look at what they had just thrown away. And when it finally arrived in the summer of 2015, what it sent back did not confirm the decision made in that conference room. It shattered it. We expected a dead rock, a frozen, cratered corpse drifting silently at the edge of everything. Instead, we found mountains taller than the Rockies made of solid water ice floating. We found red snow falling from a black sky. We found a heart the size of Texas, slowly breathing, churning, consuming anything that touched it. And now, in 2025, something even more unsettling has emerged from the data. Something that has forced planetary scientists to quietly reopen a question they thought was closed forever. Pluto may not be dead at all. In fact, according to current thermal models and new spectroscopic analysis from the James Webb Space Telescope, Pluto may be more geologically active right now than anyone in that Prague conference room ever thought possible. If that is true, and the data suggested increasingly is, then everything we use to define a living world needs to be rewritten from scratch. Stick around, because this is where it gets impossible. To understand why this discovery is so destabilizing, you need to understand what we actually knew going in and how confidently we knew it. When New Horizons launched in January of 2006, the scientific consensus on Pluto was simple and nearly unanimous. Small body, frozen solid, geologically dead for billions of years. The logic was straightforward. A world that's small, that far from any significant heat source, would have radiated away whatever internal warmth it was born with long ago. The physics were clean, the math was settled, there was nothing left to surprise us. That confidence lasted exactly until July 14th, 2015, at 7:49 in the morning Eastern Time, when New Horizons made its closest approach and the first high-resolution images began coming in. The feature that stopped everyone cold was Sputnik Planitia, a basin roughly 1,000 kilometers wide, sitting directly across Pluto's equator, filled edge to edge with nitrogen ice. That alone was not the shock. The shock was what was missing. In 4.5 billion years of solar system history, not a single measurable impact crater had formed on its surface. Statistically, that is nearly impossible for a passive, dead world. Every inert surface in the solar system accumulates craters over time, the way a parked car accumulates dust. The fact that Sputnik Planitia had none meant only one thing: something was actively erasing them. That process is called convective overturn. Think of it this way: beneath the surface of that nitrogen glacier, heat rising from Pluto's interior is slowly driving circulation like a pot of extraordinarily cold, extraordinarily slow-moving soup. The surface folds over itself. Craters sink. Evidence disappears. A dead world does not do that. And here is where the data from 2023 and 2024 begins to make the story significantly more complicated. Here is the problem that no one in planetary science has cleanly solved. Convective overturn requires heat. Heat requires a source. And when you run the numbers on Pluto, its size, its mass, its distance from the Sun, its estimated composition, the amount of heat it should currently possess is not enough. Not even close. The radiogenic heating from its rocky core, the slow decay of elements like uranium, thorium, and potassium-40 produces a quantity of thermal energy that most models agree is insufficient to drive the level of surface activity we are observing. The budget does not balance. And in physics, when the budget does not balance, it means one of two things. Either your measurements are wrong, or your assumptions are. The measurements have been checked, repeatedly. So the assumptions are wrong. The question is, which ones? The first assumption under pressure is the interior structure of Pluto itself. The classical model treats Pluto as a relatively uniform body, a rocky core wrapped in ice, frozen through and through below the outermost layers. But the geometry of Sputnik Planitia challenges this directly. That basin sits almost perfectly at the point on Pluto's surface that is tidally locked facing away from Charon. The probability of that being a coincidence is vanishingly small. The far more compelling explanation is that when the impactor that created Sputnik Planitia struck, Pluto physically reoriented itself. It rolled to bring that mass anomaly into gravitational alignment with Charon. For a completely solid frozen body, that reorientation is essentially impossible. For a body with a mobile subsurface layer, a liquid or partially liquid interior, it is not only possible, it is expected. This is what planetary scientists refer to when they discuss Pluto's subsurface ocean hypothesis. Not a warm, sunlit sea, something far stranger. a dark, pressurized layer of liquid water, possibly mixed with ammonia as a natural antifreeze, sitting between the rocky core and the overlying ice shell at a depth of perhaps 100 to 150 kilometers. Ammonia lowers the freezing point of water dramatically, potentially keeping that layer liquid at temperatures approaching negative 100 degrees Celsius. The second assumption under pressure is the timeline. We have been operating on the presumption that whatever made Pluto interesting happened billions of years ago and stopped. But the absence of craters on Sputnik Planitia is not a historical artifact. It is present tense. Whatever is erasing that surface is erasing it now. And that is precisely what the models cannot fully account for. The heat is not there, at least not in the quantities our equations predict. Yet the activity is undeniable. Something is providing energy to this system that we have not yet correctly identified or measured. That gap between what the physics predicts and what the data shows is not a minor rounding error. It is an open door, and what might be standing on the other side of that door is the question that is quietly keeping a number of planetary scientists up at night. Let me pull this closer to you for a moment. Everything we have discussed so far, the convecting glacier, the hidden ocean, the unexplained heat, is happening approximately 3.6 billion miles from where you are sitting right now. It is easy to file that away as something remote, something academic, a puzzle for scientists in conference rooms with whiteboards and grant proposals. But consider this. The nitrogen slowly churning across the surface of Sputnik Planitia is the same nitrogen filling your lungs right now. 78% of every breath you take is the same element currently moving in slow cold waves across a world at the edge of the solar system. You are not observing something alien. You are observing a distant mirror. The water that may be sitting liquid beneath Pluto's ice shell, kept from freezing by pressure and chemistry, operates on the same molecular principles that keep the fluid in your cells from crystallizing when your body temperature drops. Life did not invent these mechanisms. It borrowed them from chemistry that existed billions of years before the first living thing appeared anywhere. And the radioactive decay warming Pluto's core, that process is not unique to distant worlds. Your body contains potassium-40, a naturally occurring radioactive isotope. Right now, approximately 4,000 atoms in your body are decaying every single second. You are, in the most literal physical sense, a warm body for the same reason Pluto is a warm world. This is not poetry, this is chemistry. And this is precisely why the question Pluto is forcing us to confront is not really about Pluto at all. It is about the assumptions we carry into every room, every equation, every classification system we build. We decided Pluto was dead before we had the instruments to check. We drew the boundary of what a living world could look like, based entirely on the one example we had, Earth, and then we applied that boundary everywhere, confidently, for decades. If Pluto, at the coldest and most isolated address in our solar system, can sustain geological activity that defies our models, then the boundary we drew was not a scientific conclusion. It was a failure of imagination, and the universe, as it tends to do, has been patiently waiting for us to notice. To be fair, and fairness matters enormously here. Not everyone in planetary science is convinced. There is a serious, well-reasoned counter-argument, and it deserves to be heard fully before we move past it. The skeptical position goes something like this. Everything we are interpreting as current activity could be the residual signature of ancient events, the smoothness of Sputnik Planitia, rather than indicating ongoing convection driven by present-day heat, might reflect a period of intense activity that occurred hundreds of millions of years ago and has since slowed to a rate too gradual for our current models to detect as definitively modern. The reorientation of Pluto toward Charon could have happened once, long ago, and stopped. The subsurface ocean, if it exists, could be a slowly freezing remnant, not a stable, persisting feature, but a dying one. A world not actively alive, but not yet finished dying either. This is a legitimate scientific position. It is held by serious researchers. It cannot be dismissed. But here is where the historical record becomes instructive. In the 1960s, the dominant view among planetary scientists was that the Moon was geologically inert, a dead, unchanging body whose surface had been fixed for billions of years. When Apollo 11 returned lunar samples in 1969, analysis revealed volcanic basalts that had solidified far more recently than the prevailing models predicted. The Moon had been active significantly later into its history than anyone had calculated. The confidence was misplaced. The data corrected it. In 1977, Voyager 2 flew past Europa. The expectation was a cratered, frozen, unremarkable surface. What the cameras returned was something that generated genuine confusion. A surface nearly devoid of impact craters, crisscrossed with fracture lines, suggesting a body of liquid water moving beneath a thin ice shell. No one had predicted it. The models had not allowed for it. Europa simply did not care. In 2005, Cassini detected water vapor and ice particles erupting from the south pole of Enceladus, a moon so small it could fit comfortably inside the borders of France. Every prior assumption about bodies that size and that far from the Sun said that was impossible. Enceladus had not read those assumptions. The pattern is consistent, and it is damning. Every time we have drawn a firm line around what a small, cold, distant world is capable of, the universe has eventually handed us data that erases that line entirely. The universe does not negotiate with our models. It simply continues operating, indifferently, according to rules we are still in the process of learning. Pluto is the latest entry in that pattern. It will not be the last. Now we arrive at the question that no one in this field can avoid, even though many would prefer to. If there is a liquid ocean beneath Pluto's ice, pressurized, chemically complex, potentially stable across geological timescales, then the conversation can no longer remain purely geological. It has to go somewhere more uncomfortable. Here is what the data actually permits us to say, carefully and precisely. On Earth, life has been found in environments that were, until recently, considered categorically uninhabitable. Hydrothermal vents at the bottom of the ocean floor, where no sunlight reaches and temperatures exceed 300 degrees Celsius. Hypersaline lakes buried under 4 kilometers of Antarctic ice, isolated from the atmosphere for potentially 15 million years. Acidic hot springs with pH levels approaching zero. In every single one of these environments, when we looked, we found life, not fossilized remnants, living, metabolizing, reproducing organisms. The organisms found in subglacial Lake Whillans in Antarctica are surviving in liquid water at temperatures near -2 degrees Celsius under approximately 800 meters of ice, in complete and permanent darkness. They are not merely surviving, they are running full metabolic cycles, processing carbon, reproducing. Now consider Pluto's subsurface ocean against that baseline. The conditions are more extreme, without question. The temperatures are lower, the pressure dynamics are different. The chemical environment, rich in ammonia and potentially methane derivatives, presents challenges that no known Earth organism currently faces in combination. These are not small differences. They are significant. This is where the line between data and speculation must be drawn clearly and held firmly. There is no evidence, direct, indirect, or suggestive of biological activity on or beneath Pluto. None. The honest scientific statement is not that life exists there. The honest scientific statement is that the conditions required for life as we understand its most extreme expressions are not, on current evidence, categorically absent. That is a very different claim, but it is not a small one. Because if the threshold for liquid water, chemical complexity, and an energy gradient, the 3 minimum requirements most astrobiologists agree on, can be met at Pluto, then we are not talking about a rare exception at the edge of the solar system. We are talking about a principle, and principles by definition do not stop at the boundary of one solar system. So where does this go from here, and how long do we have to wait for an answer? The honest response to that question is uncomfortable. We are not close, not by any reasonable definition of the word close that applies to human timescales. New Horizons, the only spacecraft to have ever visited Pluto, is currently traveling deeper into the Kuiper Belt, moving away from Pluto at roughly 35,000 miles per hour. It is not coming back. Its instruments are still returning data about the outer solar system environment, and that data continues to be scientifically valuable. But its chapter on Pluto specifically closed in the months following the July 2015 flyby. What we have from that mission is what we have. There will be no follow-up observation from New Horizons. The next logical step, a dedicated Pluto orbiter, ideally carrying a radar system capable of penetrating the ice shell and directly detecting a subsurface liquid layer, was formally identified as a high-priority target in NASA's Planetary Science Decadal Survey published in 2020. That survey, which sets the scientific agenda for American planetary exploration across a 10-year window, ranked a Pluto orbiter mission among the most scientifically compelling destinations in the outer solar system. It has not been funded. It has not been designed beyond preliminary concept studies, and even if a mission were approved and funded tomorrow, the minimum flight time to Pluto using currently available propulsion technology is approximately 9 to 10 years. That means the earliest a dedicated orbiter could conceivably reach Pluto is somewhere in the late 2030s, with the 2040s being a more realistic expectation. An entire generation of children alive right now will reach adulthood before we have the data to settle the questions raised in this video. What we do have access to, in the much nearer term, is the James Webb Space Telescope. Since becoming fully operational in 2022, Webb has been conducting spectroscopic observations of Pluto's surface and atmosphere, mapping chemical compositions with a level of precision that was not previously possible. Results from these observations, covering the period between 2023 and 2026, are expected to be published in stages over the next 12 to 18 months. That data will not tell us whether Pluto has an ocean, but it will tell us significantly more about the chemical complexity of its surface, and chemical complexity in astrobiology is always the first thing you look for before you ask the larger question. We are, in other words, at the beginning of a very long answer. In 2006, 424 people voted on the identity of a world. Pluto was not consulted. It did not adjust its orbit. It did not slow its glaciers or quiet its interior or stop whatever process has been running beneath its ice for 4.5 billion years. It simply continued, indifferent to the conference room in Prague, indifferent to the headlines, indifferent to every textbook that was quietly updated to remove its name from the list of planets. That indifference is not a small thing. It is, in a way, the most important scientific instrument we have, because every time we have been certain, truly, institutionally, textbook, certainly certain about what a world is capable of, the world in question has eventually returned data that made that certainty look premature. Not wrong in a catastrophic way, wrong in the quieter, more humbling way that science actually progresses, one assumption at a time, one mission at a time, one image transmitted across 3 billion miles of darkness that shows something no equation predicted. We do not know if Pluto has a liquid ocean beneath its ice. We do not know if that ocean, if it exists, harbors any form of chemistry complex enough to be called life. We do not know what is providing the energy that current models cannot fully account for. What we do know is this: a world we declared dead is showing us evidence that the declaration was premature. And the universe, which has never once adjusted itself to fit our classifications, is under no obligation to stop surprising us. Pluto will still be there in 2040, still orbiting, still churning, still keeping whatever it keeps beneath 4 billion miles of dark. The question is whether we will have the patience and the funding and the humility to go back and actually ask it what it knows, keep looking up, and stay genuinely curious.